Welcome back. It's fourth day of the lecture.
So today I'm going to talk about a different topic, which is the topic that is perhaps a little bit easier to talk about than today, and also maybe more applicable to people. So that's the concept of VC dimension and perhaps the part of VC dimension. So today I want to discuss some facts around graphs upon a VC dimension and perhaps regularity lemma for the graph as preparation for tomorrow's talk, which is the Erdős-Hajnal results for graphs upon a VC dimension. Okay. So let me just recall definition of the VC dimension of a family of sets. So setting in this talk will be, so we have a graph set. Of course, here, since we are doing discrete math, most of the time is finite, and today there's no exception, usually finite. And actually, it's just a family of sets. Possibly empty, but in most of the cases, I think this family is going to be non-empty. So let me say, I said that S of B is shattered by F if for every subset A of S there exists some member F from the family such that the intersection of S with this member is exactly A. In other words, where this means our set of S or family of subsets of S. Okay. And the VC dimension of this family, and perhaps maybe I should say with respect to this ground set V. So is the maximum size of a subset of V shattered by the family. So, okay, so far so good. Yeah, so this notion seems to be very useful in a number of branches of pure and applied mathematics, maybe discrete geometry, computational geometry, combinatorics, of course, and machine learning, statistical learning, and maybe real algebraic geometry. So there are a few branches in math where this becomes an important role. And in today's talk and tomorrow's talk, I would like to focus on the notion of the VC dimension of a graph. So VC dimension of a graph G.
Recording in progress.
Is the VC dimension family of the open neighborhoods of the vertices of G. And of course, again, we're expected to the ground set, which is the vertex set, of G. Okay. Yeah, so there are many examples arising from in graphs with geometric constructions. Such that so again, so this notion seems to capture lots of graphs arising from geometric constructions. So, for example, I can say in the second graph, perhaps of segments in the plane. Segments on the plane will be boxes. Intersection graphs of curves, where there will be two curves cross each other about a number of times. Or that example, or more common example, may be the concept of semi-algebraic graphs. On complexity. Well, so all of these, depending on the parameter given, for example, in this case, in the intersection graphs of curves where every two curves meet each other about a number of times, these all have bounded BC dimension, where the BCD dimension it depends on this bound on the number of intersections, and also semi-algebraic graphs of bounded complexity also have bounded BC dimension, where again the dimension depends on the complexity even. Okay, so there are many examples coming from geometry and perhaps algebra. And actually, there are. So as you can see, this concept, this concept of BC dimension of the graph, right, is defined by using concept of the BC dimension of a family of sets, right? And in this case, that's the family of the open neighborhoods of vertices of G. But in fact, there are a couple of ways to define a BC dimension of a graph by using just graph theoretic notion only. And one of them is the concept of bigraphs and by induced copies of a given bigraph in a big quantity. So let me say the bigraph is a graph with a fixed partition. So the reason here is because a party graph can have many partitions, right? For example, you take a graph with no edge, then you can, no matter how you partition the vertex of the graph, then you're going to get a partition. Yeah, but here, whenever I talk about bigraph in this talk and maybe tomorrow, I will always assume that this is a party graph with a given partition. And so for the bigraph H, the graph G, bi contains H. So here, a bigraph H, as I said, is equipped with a fixed partition, E1 H and B2 H. So here, G bi contains H, or H is a bi by induced subgraph of G if there exists an injection phi from the set of vertices of H to the set of vertices of G, such that for all U in the first part of the partition of H and V in the second part, phi U, phi V is an edge of G, if and only if UV is an edge of H. Okay, so the idea here is, let's say this is a partition of H. What by induced means here is you can actually embed this picture into the host graph G such that you keep the adjacencies of the pairs between the two sides, and you don't care what's happening inside V1H or V2H. Okay. So for example, if you start from the partition of the four vertex path, let me say this is A, B, C, D, right? Then this graph X, Y, Z, T by contains this graph, right? Because here I don't care what's happening between X and Z. Okay. Right. So we're going to start the lemma. So for every D, at least one say there exists a bigraph H such that G by contains H, then this BC dimension is obviously, okay, so this is let me say and yeah, but the second statement is a bit more non-trivial. So for every bigraph H, there is this number D, that is one, such that if the BC dimension G is at least P, then G by contains H. Right. So the first one is trivial because you can just take H to be the bigraph with one side having D vertices and the other side having two to the D vertices. Right. Each vertex on the bottom has its neighborhood, a unique vertex subset at the top. Right. So in that sense, this graph has this bigraph has BC dimension exactly D. And so if any graph G by contains this bigraph, then the BC dimension of G is also at least D. Okay. So the non-trivial part is to quote the second statement. Okay. So first of all, then H has a partition V1 and V2. Right. And of course, I may assume that size of V1 is equal to the size of V2, right? And I mean, I can just enlarge, even the smaller side, not the two. And let me say this size is 3. Okay. So now I'm gonna show that if I choose D to be A plus, okay, so maybe I should assume D to be integer. Okay. I'm gonna show that this D is gonna satisfy the second claim, the second claim of the lemma. Okay. So claim okay, so here we are now. So for the moment, this is 1, this is the 2. Right. Now my job is to try to embed a by-induced copy of this bar graph into my host proxy. Okay. So what I want to do now is to look at the neighborhoods of the vertices of V2 inside V1. Yeah, so it could be that some vertices in V2 will share the same neighborhood in V1, but that's not going to be a big deal. But the point here is, with this D, if the BC dimension of G is at least D, then there's going to be a vertex subset of this size shattered by the neighborhood of the vertices of G. So I'm going to take such a shatter set. Let me say S. Here the size of S is K plus log 2K. Okay. And I'm going to arbitrarily partition S into 2 sizes. Let me say maybe S1 and S2. S1 has size exactly K, and S2 has size exactly log of 2K. So S1 is K, S2. So log of 2K. Yeah, so the reason that I need log of 2K here is because if S2 has size exactly this, then there's going to be at least 2 the log 2K, which is 2K subsets of S2. Right. So now both B1 and S1 have size K. So I can take an arbitrary bijection from B1 to S1. Let's take one. And then I look at the images of the neighborhoods in B1 inside S1. So in other words, I want to map these neighborhoods from B1 to S1. So now what's left to do is to find suitable copies of the vertices in V2. Okay. So now, so these neighborhoods, so now I'm going to look at, the images of the neighborhoods, and I want to assume, I want to look at those which are pairwise different. Right. So here, an image of any neighborhood of V1, any neighborhood in V1 inside S1 may be repeated several times, but that's not going to be a big deal. So now for each such set, let me say P. I'm going to take P together with all, take the union of P together with all the subsets of S2. So for each P representing some neighborhood, in P1, I looked at only P union R, where R is a subset of S2, right? And of course, the number of, the size of this family is at least 2K. Okay, and since this set S is shattered, I can find at least, and so I can find 2K vertices, right? 2K distinct vertices in G, whose neighborhood whose neighborhood have intersections with S exactly this family. Okay, so for each, let me say this R and this P, I can find somebody in the graph G. That vertex might be inside of S, maybe outside of S. I don't know, but in the section of this neighborhood in G with S is exactly P union R. Okay, and this holds for every R. The point here is I need 2K because these vertices might live in S1, but the size of S1 is exactly K. So what I can say is there has to be at least K vertices in VG minus S, right? Such that let me say K vertices new speed, so K vertices V, such that in the section V minus S1, such that the intersection of the neighborhood of V together with S is exactly P union R for some subset of S2. Okay. And this is true for every P representing some neighborhood inside V1. So right, so now all what's have to do is to greedily embed the vertices of V2 into these vertices. So, for example, here I have a vertex. This neighborhood is exactly P union R, another vertex. This neighborhood is also P union R prime. Yeah, but I don't care. But now I don't care about what's happening inside S2. What I only care is there are at least K vertices whose neighborhood have intersection with S1 at exactly P. So now for each vertex in V2 whose neighborhood in V1 is the one that gives P, I'm going to embed this vertex into one of the selected candidates here. And I can keep going because I always have at least K choices for each such vertex in V2. Okay. So now quickly embed.
Oh, I missed that part. So so you're worried about the situation where two vertices in V2 have same neighbors?
Yeah.
How do that?
Use a different R prime, right? Like in S2.
Yeah, the different upfront. So
Oh, okay, okay.
Yeah.
Like, I have a question. Why do you need a 2 to the I mean, log 2k instead of log k?
yeah, because there might be some vertices in S1 whose neighborhood is exactly P union R. And yeah, I mean the definition is we only look at the neighborhoods of the vertices, but we don't know where the vertices are.
Yeah, but it's isn't S on one side of the pie graph?
No, I
Because-
mean actually it's a set of the host graph.
Yeah, but S is shattered and it's shattered inside like part like.
Scattered by the neighborhoods, so the vertices giving the shatter property by leaving S.
Um. Oh. I see.
Does that make sense? So I want to get rid of those possibly leaving in S1.
Uh-huh. So that's,
Yeah, so that's the purpose of 2K.
so you have, if you have a,
Okay, so if someone in S1
right,
whose neighborhood in G intersect S at exactly P union R,
uh-huh,
then I cannot embed any vertex
Right.
of 32 into it, right?
right.
And so I have to get rid of it.
So are you saying that if you have two such vertices, then one of them should be out of S?
There's two K vertices.
There are 2K vertices giving this
That
P
S1
union
has
R.
ice K.
Oh, okay.
The size of S1 is K.
I see.
So there are at least K vertices outside of S1 giving this P union R.
Mm,
Does that make sense?
okay. I see. Mhm.
Any other question?
This previous two basically says phi containment is equivalent to bounded.
This dimension, exactly. That's actually what the lemma is.
Yeah, but I initially thought the limits map V1 to S.
Yep.
Map
the neighborhoods. Yeah, so I map B1 to S, I mean, which carries the neighborhoods into S as well.
right.
In S1 actually.
So that means you were assuming that S is completely in V1 side of G.
Yeah, supposed to be.
But the VC dimension doesn't guarantee that it's on V1 side. It could be on the other
Exactly,
side, right?
yeah. Because the definition only tells you about
Yeah.
the neighborhoods. It doesn't tell you about the vertices.
Mhm. And so shattered set cannot have a vertex on both sides is it because of the like physics by pattern. So that's what.
Yeah.
I mean, what I thought is that when you have a shattered set,
Yeah.
that it's on completely on left hand side or right hand side.
No,
Because-
it's not left hand side or right hand side. I mean, a shattered set is simply a set shattered by the neighborhoods. And there's
Yeah.
no left and right here.
graph G isn't G a bi G is also a bigraph, right?
No, G is a general graph.
Oh, G is general graph. Okay, so. Uh-huh.
Yes, so in this series of talks, I mean, G is always a big post graph with no given property, except for the fact that it might have some covenant induced subgraph.
I mean, when you define a bigraph, a bi-induced subgraph, you define it for two bigraphs.
No, I think it defined for
Oh, G
the graph
contains.
G by content.
Oh, all right. That's the computer. Mm.
So, I'm so sorry for any possible confusion. Right, so yeah, so this is a characterization of graphs of bounded VC dimension in terms of bi-induced subgraphs, right? And but the point here is, I mean, if you pair about exact induced copies of a given graph, then this characterization is not satisfying, right? Because here we have bicontains, and there might be still many edges living inside one of the two sides of the graph H, and so the number of user graphs that we need to exclude, is potentially huge in terms of the size of H. But in fact, there is actually a characterization saying that we can reduce this configuration into just 3 configurations, and we can do induced. So let me the definition. So I guess we are all familiar with bipartite graphs. So we call bipartite graph is just a complement. Bipartite graph. And the split graph is a graph whose vertex set in addition into clique and independent set. So again, bipartite is like partition into 2 subsets where each of them is independent. So this is bipartite. Co-bipartite means partition into 2 cliques. And split means one is split and one is independent. So I have another one. This is going to be similar to this characterization, but now with induced subgraphs instead of by induced subgraphs. Again, that will give you one. Which is bipartite H1, co-bipartite H2, split J, such that H1, H2, and J3 is VC dimension almost D. Sorry, such that G has 1 H1, H2, and J as user graph, then you see the dimension of G is this. The second is bipartite H1 over bipartite H2, and split J theoretically at this one, such that this is the dimension of if the DC dimension of G is at least D, then the has 1 H1, H2, and J induced graph. So in other words, we can actually characterize graphs upon a fixed dimension by using only three forbidden induced subgraphs. In three kinds of forbidden induced subgraph. One is a split graph, one is a bipartite graph, and one is a co-bipartite graph. Okay, so again, this first statement is easy, just like this first statement here. Not a big deal. The second one is a bit harder. I think I'm going to sketch the proof because it's not going to be much relevant for tomorrow. And also, the proof is a nice application of the Erdős-Hajnal bound. And so, sketch for a second. So here I'm going to use two results which will be given as exercises. Exercises. First one is the result of Erdős-Hajnal impact. From 2000, I think. But for every graph, for the bigraph H, and bigraph F. Here, the bipartition is B1, B2, and the bipartition of F is X1 and X2. Okay, so if F does not bicontain H, where B1 is a subset of X1 and B2 is embedded into X2. Then there exists Y1, X1, Y2, X2. The Y1 is at least X1 raised to the power of C, then Y2 is at least X2 raised to the power of C, where C is some constant depending on the H only, such that Y1, Y2 are complete for and complete to each other. So, so what this means in this first result is this is X1, this is X2, and then you can shrink X1 by a polynomial factor, and you can shrink X2 also by a polynomial factor. So this is Y1, this is Y2, and here either all edges between Y1 and Y2 appear, or none of them is present. So, yeah.
So I have a question for this lemma, for this split thing.
Yeah.
The second bullet point is the whole purpose, is it just so that compared to the previous one, we want to gain more control of what's happening on top and bottom?
Exactly, that's why I said. Yeah, so we want to know, we want to reduce the number of possible forbidden induced subgraphs. Yeah, exactly. So this is a more refined version of the second result in the previous lemma.
Do you really need this polynomial thing in order to prove the second lemma?
Probably not. Yeah. But I mean this, but for me this is a nice result, and compared to the usual this kind of result for general graphs, then this is much more simple. Much more simple. Okay. And
Excuse me, if our split graphs are bipartite graphs split?
I think the only case is all induced subgraphs of P4.
The answer is no in general. Right?
Yeah, the answer is no in general.
Uh,
So split graph. So a graph is split if the vertex set can be partitioned into a clique and an independent set. And yeah, not all, but and. Is that clear? And if you want to find all graphs that are both split and bipartite at the same time, then they have to be induced subgraphs of the four vertex path.
What is the symbol? Click something and maybe.
Yeah, that means and. I often use this notation, but maybe not be a good choice after all.
One side has one vertex and it's,
Which country?
then it's split and by one vertex.
Yeah, oh, yeah, that's true. Thank you. Yeah, so the stars and yes, maybe a good exercise to characterize it. Anyway,
So I have two more questions. One is more same as Sunny. Which country do they use this and?
I have seen this from, first of all, Vietnam, of course. And maybe some people in the US. I don't quite remember, but yeah, but I guess this notation is. I think this notation is also in.
So that's not F.
Yes, no, it's not. So maybe just my bad hand writing. I think that's also on the keyboard.
Oh, but that one is like this.
Yeah, but
It's different order.
yeah, it's a different model. I'm so sorry about that. Yeah, so you're right. I mean, if you want to, so back to this business, if you want to use, you just want to prove the second statement, then perhaps this polynomial bound is not exactly needed, but still it is a nice result. So
Another question is there a multi-factor version? Let's say you define tri-containment, and now you forbid something as tri subgraph.
that's a very good question. That is related to the conjecture of Fox and Sulakov. So the problem arises when you try to forbid a triangle, a rainbow triangle.
Maybe I have to later then.
Yeah.
So it's not no. The short answer is it's not no.
Yeah, I think. Or maybe I'm lying because I need to read in some memory, but as far as I know, I made the question for 3 parts and already see one should be. We can clarify that later. Okay, so that's the first statement. The second statement is I think it should be a cup of tea. So if there exists, and let me say for every lot and there exists by graph H with V1 and V2 and no Y1 subset V1 Y2 subset V2 with Y1 Y2 is 2 lot and Y1 Y2 repeat or I think complete in each other. Okay, so this is just done by taking a random but positive. So if you're familiar with the first moment method, then it should not be a big problem. Right, so let me try to use this. Okay, so these are going to be a very quick proof by a picture. Yeah, so from the second statement of this lemma, right? So it's just, so it suffices to find a bigraph H, so that if the graph G bi contains H, then it's gonna contain H1, H2, or J as induced subgraph, right? So suffices to find the bigraph H such that, in other words, if G is H1, H2, J, 3, then G has no by, let me say G doesn't. Doesn't I continue? Right? And so this is done as follows. So from the second exercise, you can find a huge bigraph H, right? I mean, with no complete or incomplete pair size about log n. Okay, so here we are. Bigraph H. This is B1. This is 2, and no complete or incomplete size for log n. So now, let's suppose that G bi contains this bigraph H. Okay. And with the assumption that G is H1, H2, and J3, you can use the Erdős-Hajnal bound, right? Now we look at what's happening inside V1, and what's happening inside V2, and here V1 and V2 have size n. So since G is H1, H2, and J3, from V1, you can get a clique or independent set of size at least 2 to the C with log n. Right? This is what the Erdős-Hajnal bound is. From V2, you can also get a clique or independent set of size 2 to the C with log n. Right? So let me say this is S1, it's S2. So S1, S2, or independent set size, and this should see log n. Okay. So now, let's suppose that just to make it a bit more complicated. And then let's assume that S1 is a clique and S2 is an independent set. Okay. So so here I think I said that J is a split graph. Right? The J is a split graph, and the vertex set of J can be partitioned into J1 and J2, where J1 is a clique and J2 is an independent set. So if you look at the bipartite graph between S1 and S2 in G, then what this means is this bipartite graph does not bi-contain the bipartite graph between J1 and J2 in J. Right? Because if there is a mapping from J1 to S1 and a mapping from J2 to S2, that preserves the adjacency, or in other words, preserves the edges and the non-edges, then we're going to get an induced copy of J in G. Is that clear? So what this means is the bipartite graph between S1 and S2 in G does not bi-contain the bipartite graph between J1 and J2 in J. So by the first exercise over there, you can shrink S1 to the subset S1 prime and shrink S2 into subset S2 prime with the property that S1 prime, S2 prime have size at least 2 to the C root log n. And maybe I should use C prime now, raised to the power of C prime. Where here C prime depends on J. Okay. This is 2 to the C times C prime root log n. And such that S1 prime and S2 prime are complete or incomplete to each other. But now the issue here is this function is much better than log n. Right? It is much bigger than 2 log n. And so this contradicts this property H as we got from the beginning. That's the contradiction.
So I'm confused. Are you putting the second bullet point there of that lemma?
Yeah,
So, you want to say, if you do not have these 3 things as induced subgraph,
yeah.
then you also, can you have large visit dimensions?
But I cannot have large visit dimension.
All right, you cannot have two, right? Now, how do you get this no complete or anti-complete pair of at least 2 log n?
No, that's the second exercise.
Oh, so he's not proving two, but you're proving
I'm proving it.
Second lemma.
Yeah. Right.
by using the,
Two exercises, both explained.
by using 1 and 2, he's proving. So this is consequence, so just take H from the second.
Oh, so what's written there is for H.
Yeah,
So the no complete or anti-complete pair is for the.
yes, for H, yeah.
For H.
So H already, we already know, assume that H has the subgraph. And then,
So in other words, you can start with a big random, the partial graph. Right. Then with our probability, there's no complete or incomplete pair. Applies to log n. I will treat that as H. So now I'm going to claim that if G bicontains H, then it's going to contain one H1, H2, or J as induced.
So the little n is not order of G, right? It
Exactly.
goes H.
Yeah, so now it is, yeah, so it's confusing, yeah, very sorry about that, so let me say. So just to make sure that it's not decided here, yeah, you're right, yeah.
So I guess this is a different notion of bicontained. This is what I'm gonna, like in exercise 1, they're both bigraphs actually.
Yeah,
So, yeah, and this is.
that was what I was imagining.
yeah,
If you just use Ramsey's theorem and the simpler thing, then you still get the second lemma, but with the wrong, with the poor power, right?
yeah.
So then how do we finish the proof? Right? So we take H such m vertex graph that does not have logarithmic,
Complete right, complete right, yeah.
and after that,
And after that, I show if if G bicontains H, then it can contain one of these 3 graphs as induced graph. It's an induced graph.
okay, you prove the contrapositive again.
Yeah.
I see. Okay,
So by
now,
like you click or stem set in each side.
Yes,
and then on each side, you use
Hajnal theorem. The Erdős-Hajnal bound.
Right.
Because now the whole graph G is supposed to be these 3.
And then after that, you use this Erdős-Hajnal path,
Yeah, exactly.
but apply to one of these H1, H2, right? Or
Apply to this S1,
S1 is
S2.
still.
S2, and then what's the forbidden thing now?
The forbidden thing now is the J1.
Yeah, if one of them is independent, the other is deep clique, then you look at J, right?
Exactly.
If both are independent, you look at H1.
Mhm.
If both are clique, you look at H2.
I see.
So maybe you have the 10 minutes break.
Okay, it's about time. Is a recording continuing? Okay, let's resume.
So so let me now go to the which has strong regular dilemma for graphs of one dimension. And let me start with the definition. So we have a graph G in a parameter epsilon and as usual, ranging from 0 to 1/2. And let me say ultra strong, epsilon regular addition. G is a partition. B1, B2 to BL region such that the utmost an epsilon fraction has BI BJ. Here, of course, we have by distinct and J and except L. Epsilon pure. So what does this mean? This means number of edges between BI, BJ, G is either at most epsilon times the product size two subsets, or at least 1 minus epsilon. The product. So, yes, so in other words, the density between BI and BJ is either at most epsilon or at least 1 minus epsilon. Okay. And this is true for all the epsilon fraction pairs. So here's the ultra strong regularity lemma for thousand by the preceding dimension by the buttons that they so the theorem by the buttons that they around and it says for every BX one there exists in K first element B. Let me at least you provide and the inequality is two such that every graph G BC dimension almost D that is ultra strong every graph G the BC dimension such that also here epsilon so for every epsilon from 0 to 1/2 and every graph G BC dimension almost D G has an ultra strong epsilon regular E3 partition. One with two L where L is an integer, possibly depending on G, but L is between epsilon inverse and epsilon to the minus k. And here by equipartition, I mean size difference, EI of BJ equals 1 for all I except for in other words, you can say you can deduce that each PI is of one of two values.
So how does K look like right?
Oh,
The
yeah,
current
so, yeah, that's a good question. I think the group, so I think the group can give you K equal something like 40, 2D 40, so that's it's pretty good. Linear in the. I'm not sure if you can even do K equal D, but let me say K point is possibly maybe 40 or 80. So
And from below, their example showing that linear in D is necessary.
that's a good question. Yeah, but I guess in practice we don't think about the dependence. Any question? So yes, in the last 15 challenges, I try to sketch a proof of this, but if I am not done, then maybe I'll try to go tomorrow as well. So yeah, but it's a question about this statement. Okay. So a bit about the history of this result. This theorem was proved first by robust and Jacobi using graph forms, and there was an earlier version of Alon, Fisher, and Newman called quasi graphs. But this result is the most of the result. The first proof was done by graph forms, and the proof that I'm going to present is by Jacob Phelps, and Erdős. So by Max around 19. Yeah, proof is pretty simple. We're using a weak version of auxiliary spectrum lemma. Yeah, so using how does it look like? So I have a question. I mean, is everybody here familiar with the social Laplace lemma? Obviously, raise your hand if you haven't heard it.
Haven't heard.
I haven't.
So I guess everybody. So I would assume that everybody is familiar with the lemma. So they have to study it. So
You can state it. You can state it.
yes, we take this in mind. Sour. So as Jim, let's say D. Then with respect to Brown set B, right? And for any B, number of intersections of members of this family with S. We have most this will be that's it. Which one? It's most S to the power D, maybe 2 times S to the power D. Yeah, but the main takeaway here is in the upper bound is a polynomial in S with degree D. And the proof of this means is going to be all of you already know it's a very simple proof by induction. So the next result we're going to need. Let me say this is written Hausler. So the main object in this lemma is going to be the symmetric difference of two sets. So let me say again that as the nothing B in relation to the master B and E1 A2 and K in family such that the symmetric difference two arbitrary sets is at least the divided by 2. So here this means AI minus DJ union DJ minus AI. And here Q is the number is one. Then K cannot be too large. And how large? K is at most some constant depending on the bounds Q log Q raised to the power D. If Q is sufficiently large, so that is the bounds. So yeah, so the real version of Hausler's packing lemma is without this log. But there is a very simple proof showing that this bound, showing this bound, and which is going to be good quality for our purpose. So, any question? The proof of this is a simple random sampling pattern.
Why this lemma is called packing lemma?
I guess you want to pack. I mean, I guess you want what I mean. My guess is you want to pack. I mean, the sets from family so that they are very different.
The AI symmetric expressed with AJ is like Hamming distance, right? So you want, you want to have Hamming distance far apart.
I don't know, in literature, they say this packing language. Yeah. I'm just following what is standard. So yes, a proof is by random sampling, and you want to sample several vertices in several members from B, and now try to see how much do they interfere with these symmetric differences. So sample. So let's see. Parameter here. So I only use K. Let me say M. Sample M elements. set it to be, so. So you want the two, you add. Independently random.
Are you proving the regularity lemma or you proving?
I'm proving this lemma first, and then I'm gonna use this lemma to prove the theorem. It's a proof for. This house. So we're gonna sample m elements from V, of course, uniformly and independently at random with repetition. Good. So something like this, S E 1, 2, 3. So now for each pair AI AJ, I want to examine the probability that S is gonna hit this symmetry difference. Okay, so the probability S in a session with the symmetry difference AJ is non-empty. Is what? So I sample m elements uniformly and independently at random with propagation. So probability, and so the probability is going to be exactly 1 minus the symmetry difference of J divided by size of the ground set raised to the power of n, right? And from the condition that the symmetry difference is at least V divided by Q, this is going to be at most 1 minus 1 over Q raised to the power of n. Okay, and I'm going to choose m later. And this is almost e to the minus m over Q. Okay. Oh, sorry, it is empty because you want to estimate the back probability. Now I'm going to do the union bound. So the union bound tells me let me take this square bounds e to the minus n with Q. Right? And now I want to choose m such that this quantity is strictly less than 1. So because of that, I'm going to say I choose m to be Q okay. Okay. So this is going to be less than 1. Is less than k squared times this and minus 1. Okay, so what this means is that exists at most n elements. Let me say t. So t with t equals n, such that t intersection with all symmetric frequencies non-empty. Okay. Any questions so far? So what does this condition mean? What this condition means is the intersection of T with the AIs are all going to be different. And yeah, so now we use storage first, solid SSD. We imply that K is at most 3 times D raised to the power of D, which is equal to most 2 times 4 Q of K raised to the power of D.
What is the first one? T intersection AI?
Yeah, yeah. So the intersection are all different because T hits all of these symmetric differences.
I see. Okay. So the T intersection AIs are all distinct.
Yeah, they're all different. Okay. So now
You don't know which side of, you don't know which one of the K intersect. Is it possible that you always hit on the symmetric difference that is some AI escape?
it will be in the
What this says that T intersection AI and T intersection AJ are distinct. For all eyes.
Yeah.
That's what
So
it is,
you-
right?
yeah, this is exactly what it means, right?
Because of this.
Maybe one with the maybe you can just draw it.
Okay.
So yes, now it is simple calculus, right? So we have K and what's this? So we have a simple calculus. So questions?
Possible strategies now both not use these landmarks actually.
So
We say that the original customers are taking landmark, there is no additional adjustment.
yeah,
That group does not use these idea or
no, I think this actually, I think the common sense is in this group should come out before the also. Maybe I guess what you want to do is to improve, is to get rid of the log term. And as far as I know, his proof is a pretty sophisticated balance algorithm. But this is simple. And enough for our purpose.
So K here is M, right? Or
No, K here is a number of subsets.
I see.
Yeah. K here is the number of
Right,
subsets
right.
in the family with a large symmetric difference.
As it basically proves says, if you have a collection of power sets, then you take a random set, the trace of this random set must be different.
Exactly.
Mhm.
Yeah, that's a very nice way to rephrase it. Oh, good. So how much time do you have?
It depends on how much time you need for the regularity.
Oh, I see. So maybe let me skip it to tomorrow.